Okay, guys. So in this session, we will start ISRO 2017 part 2. So when you look at the first question and try to answer, what is the answer for this question? This now in this one, to answer this question, we must know whether aluminum is ductile material or brittle material. So here, aluminum is what? Aluminum is ductile material. For ductile material, we have two theories of failures, right? For ductile material, the most uh, relatable or the most applicable theories of failures are maximum shear stress theory and maximum distortion energy theories. Out of these two, when we talk about you know most applicable, right? Most applicable theories of failures are maximum distortion energy theories. So D will be correct. Now the question will be why. Here the answer for this question is very simple that we can answer from graph. When you look at the graph, when you look at the graph of this sigma 1 and sigma 2, that is for 2D, you will find there is a ellipse. Here there is a ellipse for this this is for what we call maximum uh, distortion energy theory, and whatever I'm writing in the inside of that, this is nothing but so this is nothing but your maximum shear stress theory or Tresca's theory, and whatever the black color which I have drawn, this is nothing but maximum distortion energy theory. This we also call von Mises theory, and this we also call Tresca's theory. Now, when you look at this graph, from this graph only every answer we can get. Here, just look at the graph very carefully, which is giving you the more area. Out of blue line and black line, the area which is given by maximum distortion energy theories are very means larger as compared to Tresca's theory. Area of the graph of maximum distortion energy theories are more than area of Tresca's theory, right? Or we can say maximum shear resistance theory. So if you just consider any point, if you just consider any point, let me consider a point somewhat here, for example. Let me consider a point P. For a point P is very near to, or if I just consider this point P to be in the second quadrant, let's say you have applied sigma 1 and sigma 2 in such a way that sigma 2 is positive, sigma 1 is negative, and here you have value called P, point P. When you see point P, the point P is nearer to which particular line? It is nearer to maximum shear stress theory line. And when you consider the maximum distortion energy theories, these lines, this point P is somewhat far away from point P. So what the maximum distortion energy theory will say to you that he will say the factor of safety given by maximum distortion energy theories will be higher than factor of safety given by maximum shear stress theory, because point P is far from the point P. What you are looking right now is far from this particular point, this particular black line, this particular line which the black line which is being plotted by von Mises, right? So what the von Mises are saying, you are away from the failure graph. What the conversation will happen between point P and von Mises is that he will say the point P is far away from my particular failure graph, because any point above this one, if you just find that Q point is here, that means this material is already failed, right? That means point P is very, very far from this black line, but very nearer to the blue line. That means who is giving you the more alarming conditions? Who will be giving you the more alarming situations out of Trescas and von Mises? When you look at the graph, you will clearly see that the moment P crosses the blue line, suppose here, it is automatically failed by Trescas but safe by the von Mises. Then von Mises is saying that you are very, very far from failure lines. Don't take larger diameter. You can apply any amount of load, right? He will be giving you the very higher factor of safety, right? And the person who is giving you the higher factor of safety, that means it's like basically fooling you, they are not basically alarming you for the worst conditions. So that's why we also say sometimes Trescas is somewhat more conservative than von Mises. But accurate theory which is being predicted by von Mises is exactly or almost equal to experimental results what we got for the ductile material. That's why we say it is an exact or most suited theories of failure for ductile material. But when you talk about the safety purpose, the safety given by Trescas is much, much larger than the von Mises, right? Factor of safety given by maximum distortion is much higher than the factor of safety given by Trescas theory. That means the diameter given by maximum distortion energy theories will be lesser than diameter given by maximum CSS theory. Trescas will be alarming you in such a very high frequency that he will be saying you take larger diameter. You better take very, very large diameter, even though you have to put a lot of amount of money for designing the material. You put that money, you put that material, but the material should not fail at any conditions, at any cost. That's why we say it is a over safe design. Not only safe, over safe design. Unnecessarily wastage of material will be there, right? All of your understanding. So this is what we are finding, that out of maximum distortion energy theories and what we call maximum series theories. So the most applicable theories, even we found out that experimental also, whatever the results we got from the von Mises is very much suitable to what we got in experimental results, right? Because according to maximum distortion energy theories, you know that uh, tau value at the yield point is what? 1 upon root 3 times of sigma at the yield point. That means it is 0.577 times of sigma yield, right? Whatever the results we got from the yield, maximum distortion. Experimentally also, whatever the results we got, tau yield, it was approximately 0.55 times of sigma yield. But the results which we got from maximum Sayre's theory, that is, he was saying that tau yield will be uh, 0.5 times of sigma yield, which are not closer to what we got experimentally. Closer value is what, this one, right? So this is the over safe design. This we also say sometime economical design. Now, what will happen when you design the ductile material by another theories of failure? You know that we have Rankine's theory. You plot on the same graph, what you will understand. For the point P, the red line which we plotted, that is the Rankine. Rankine will say you are very far from the failure lines. Don't take that much of diameter. Even a small diameter will survive. That means he will be giving you the largest factor of safety. That is the worst theories of failure for the ductile material. Means as far as the second coordinate concerned, if you are loading in such a way that sigma 2 is positive, sigma 1 is negative, in those scenario, Rankine will give you least diameter, highest factor of safety. That means he is not at all giving you any alarming conditions. So the correct answer will be D. So by this question, I have covered theories of failure. In short, what we have discussed in our classes, that whatever the scenario I have given, that we usually discuss, right, in theories of failure. So I have discussed in short three theories of failure, that is Rankine, von Mises, and Triscus. So sometimes the question can be asked. Already they ask many questions out of this slide. Overset design, you know, economical design. They can give question by naming any other. They can pick any point from this slide and they can frame the questions. In other examination, they already frame the questions. Now, question number 6 is belonging to what we call columns. Here they have given the four columns of equal length and cross section, but with the different end conditions. Which of the following is true? So they are asking in which case critical loads will be here. Whatever the critical loads are there, that we need to find for different end conditions. Right. So try to answer this question. See, I will be telling you shortcut. In examination, you try to remember that shortcut. Right. See, first write fixed condition. Fixed pin connection. Then write pin connection. Then what you write? Fixed free conditions. You always remember what I am telling you in the same manner. You please try to remember. You will never forget. Now, this four condition you please note down. Now, so whatever the alpha value we used to write for a fixed condition, we write 1 upon 2, 1 upon root 2, 1, 2. That means in the basically you just write in the increment order whatever the alpha you try to remember. 1 upon 1 by 2 means zero point 0.5, 1 upon root 2 means 0.707, 1, 2, like that. So effective length will be L times of alpha. And we know that critical load will be what? Pi square E I minimum divided by alpha into L whole square. So P critical will be inversely proportional to alpha square, right? So here we can write whenever alpha will be more and more, critical load will be required for buckling will be lesser and lesser, right? Critical load required for basically what? For buckling will be lesser and lesser. So here for the fourth conditions, for a fixed and free condition, we require what? We require least amount of critical load, right, to buckle it. So here you just note down critical load required for both the ends fixed will be larger than critical load required for fixed and hinged. This is both the ends fixed and hinge, pin, fixed and free. Critical load required for pin connection. Critical load required for fixed and free conditions. That means the last condition will be very easy for us to buckle it. When both the ends are fixed, it is very difficult to buckle. You may require larger amount of load for that. That's why the critical load is basically what you can say what 4 times the pin connections. So while looking at the options, where is my P2? So here when you consider here when you observe, this is the fixed free conditions. fixed free conditions, pin pin connection. Here we have fixed pin connection, and this is both the ends are fixed. Both the ends are fixed. So here, what is the condition? The largest amount of load will be required for fixed conditions. Then we require for fixed pin connection. Then we require for pin pin, and the least will be required where fixed and free conditions. So we will be correct. Again, I am telling you, you try to remember the manner in which I am saying you. First, write fix pin pin fix free. Again, there is a no rule to remember, but why I'm saying, because alpha you try to remember in this, it is increasing 1 upon 2, 1 upon root 2, 1 2, and alpha sometime in some examination they ask what is the alpha. So we used to write length fixicity coefficient. The length fixicity coefficient. Okay. Again, in the one of the previous year questions session of ISRO, I told you, not only I told you prove resilience, I told you modulus of resilience. When you go back to the pages, you will find that. And I told you how to find the modulus of resilience. It is the area under stress strain diagram up to the elastic point. This is the elastic limit. Up to this, you try to calculate area. That is nothing but modulus of resilience. And modulus of resilience is the property of material. Right? So you will find the area. Area is what? Up to the elastic limit. Half of stress up to elastic limit, strain up to elastic limit. So half of this is 200 into strain, that is 0.001. So when you calculate, you will be getting answer in terms of Newton per mm square into mm by mm. So you will get the answer Newton per mm square. So let's first of all find the value in Newton per mm square. 0.1. 0.1 Newton per mm square. So here when you find zero point 0.1 into 10 power 6 Newton per meter square. Now when you convert in kilonewton per meter square, you will find it is 100 kilonewton per meter square. We will be correct. What is the modulus of resilience and all those things I have given very clearly in our one of the previous year questions sessions. I think second class when we have discussed 2016 paper. If in the same question they would have been asking modulus of toughness. If they would have been asking modulus of toughness, then calculate area under stress strain diagram up to point F. Up to point F, breaking point. Please make a note of it, because previous year question hardly repeated, but the pattern in which they have asked, that may be repeated. So this may they ask. Exactly, if you want previous year question that to be copied, then why they will conduct the exam? They will not repeat even a single question, but you have to think what the question they have asked, right? In those previous years, those questions you have to 360-degree, you have to do the analysis. Again, when you see this in question number 11, here what is they given? They have given the two material. Both the materials are dimensionally equal. That means areas are equal and length, whatever the lengths are there, the length is also equal. They are made up of material which is having Young's modulus E1 and E2. A uniform pressure P is applied over the blocks through a very thick plate AB, symmetrically placed over the blocks. They are placed symmetrically, right? For E1 is greater than E2, consider the following statement. They are saying that stress in both the blocks are same, strain in the both the blocks are same. Plate AB will be tilted, but whether they are tilting like this or like this, that they are asking. So see, what we saw in our regular cases, the beams are series combination, beams are parallel combinations. So this is what we are say, the beams are parallel combination. But here you have to remember, when you draw the free body diagram of plate AB, so that uniform, whatever the pressure which we are applying, whatever the uniform pressure we are applying over the area of AB, we can calculate that load which we are applying, actually the load which we are applying, P into area of that plate AB, so that we can get what is the it is acting like a uniformly distributed load kind of things, but it is a pressure value. So here force we can calculate by multiplying P with the area, right? And this plate will offer this two material will offer some kind of resistive force like this, F1 and F2, right? This will offer some kind of forces like this. Now both are placed just symmetrically. When they are placed symmetrically, then whatever the force they will resist, that is equal. Whatever the forces they are going to resist, that will be equal. When the whatever the loads we are applying, that will be equal, right? Here one more thing you have to remember, when we find the stress value, we write F1 divided by area 1, that is the stress in first material. Stress in second material will be F2 divided by area 2, area of the second material. Here F1 and F2 are same, whatever the F1s are there, that is same. A1 and A2, that is also same. So we can say stress, that is going to same. Whatever the stress will be there, that will be same. When the stress will be same, you know that according to Hooke's law, stress is directly proportional to strain. So definitely there is no chance of getting the strain to be equal, right? Here E1 and E2 both are unequal, right? So strain will not be equal, stress will be equal. So remember, this is not the case of beam bars in a basically what, a composite bar, where in composite bar, remember, in composite bar, when we connect or when we just place two material, when you talk about the composite bars, no doubt, two cases we have dealt, where first case we have dealt in our strength of material, that bars in series combination, bars in parallel combinations, right? So when I talk about the bars in parallel combinations, let me take this here. In bars in parallel combination, we used to see, suppose a material is there, one material is like this, inside that we are placing another material, for example. So this is the one material, let's say aluminum, it is being placed inside the steel segment, and we are applying the load P. In this case, we directly take delta of aluminum, that is equal to delta of steel, right? We say strain in aluminum, that is strain in what, steel, right? So when we say strain is equal, during those scenario, we say the bars in what, that is composite bars, right? But here this is not a very composite bar case, right? Situation might look similar, but here strain will not be equal, right? Because the plates are placed very symmetrically and the loads are also what, very symmetrically has been applied over both the plates. So stress will be equal, but here strain will not be equal. Now coming back to this, plate will be tilted in which directions? This case we have to see. So in this one, in this particular case, you understand here when we talk about the deformation in first one, that is PL divided by AE 1. P is same, L is same, A is same, right? So here that is a delta 1. What is the delta 2? P into L divided by A into E2. So here delta 1 is inversely proportional to E1. Again, we can say delta is what? 1 upon E. Now E1 is what? Greater than E2. So can we say delta 2 will be more than delta 1? When delta 2 will be more than delta 1, what will happen? This particular second material will deflect more as compared to the first one in the compressive load. Whatever the loads we are applying, both will be under compression, but the delta, whatever the second material will be there, that will be under more compressive, that will be having more compressive deformation, that will be having more deformation as compared to the first material. So it will be deflected like this. Plate will be deflected like this. So here what is happening? Point B will be moving towards the downside, or we can say here exact deformations will not be like this. Here it will be, because whatever the AB plate they have mentioned, the AB plate here, that is a, we are assuming that that is a rigid plate, right? A thick plate, that is a rigid plate. We are not assuming any kind of deformations here. So that may be deflected like this. Right? So point B will be moving towards the downside. So R and P both are correct, so the option will be correct. Right? Note down, this is important. So this is what we have somewhat good question. So for this type of question, if you are not getting any idea, try to attempt in the last. Because don't think that if you are not able to solve, uh, or if you're thinking that many other candidates will be able to solve, then it is not possible. Now, again the question from strength of material, the horizontal bar AB is assumed to be rigid. That means there cannot be any deformations. It's supported by the two wires. One wire is C and other wire is DF, having a length of L and 2L. Each wire has a cross-sectional area A. The tensile stress sigma 1 and sigma 2 in respective of, means in both the wires C and DF will be what? So again, for this we have to draw the free body diagram. When we just apply the load P, or the load P here like this, then it will try to resist. The loads will be acting in C like this, and the loads which are acting in DF will be like this. This is what we have B. The length is what here is B. Here also it's B. So what we are taking, summation of moment about A point to be 0, FCE into B plus FDF into 2B, that is equal to P into 3B. Now some of you might be thinking, sir, why there is a force C will be acting in upward direction, force DF is acting in the upward direction. See, when you just apply the load, the rod will be tilted like this. When the rod will be tilted like this, then this bar CE will be subjected to what? Tensile force like this. Right? Here also the bars DF will be subjected to what? Tensile force like this. What about the reaction force offered by this wire onto the rod in the opposite directions? So the reaction force will be acting what? In the opposite directions on the rods by the wire, right? So we are drawing the free body diagram of, not the wires, free body diagram of beam here, horizontal bar AB. We are drawing the free body diagram of not the bar, not the wires. We are drawing the free body diagram of bar AB. Now here when it is deflected, it will be deflected like this, because there cannot be any deformation. So it cannot deflect like this. It is not possible. So definitely here it will be deflected like this. So here whatever the deflection will happen in CE, it will be like this, and whatever the deflection will happen in DF, it will be like this, and whatever the deflection will be there at the end points at P point will be this. This theta will be same. So delta CE from a similar triangle, what we can write from A, name is what? AEF, AEFB, AE, this is E dash, F dash. So from the triangle AEE dash, that is delta CE divided by B, will be what? Delta DF divided by 2B. So delta DF will be 2 times of delta CE. Delta DF, how to calculate delta DF? Delta will be what? PL divided by A, but the load is what? FC, length AE. Area and the material both are same. 2 times of this, what we call FCE. Sorry, here this will be DF, DF, length is what? 2L, 2 times of FCE, L divided by AE. So from here we are getting what? FDF, that is equal to what? FCE. Put those values here. Put those values here. What you will get? FCE, that is equal to what? P. You will be getting P. FDF also you will be getting what? P. Once you got the load, area, area will, for both the materials, for both the wires are what? Same. So what will you will be getting? Stress in C will be P divided by area. Stress E, that is we are calling sigma 1. DF will be what? P divided by area. That is sigma 2. So both these stresses will be equal. P by A each. So for this type of problem, you try to see BC Purnia book, in which you try to solve solved example. Many good examples are given in that book. Good examples are given in that particular book regarding this type of problems. The problem which they have given in ISRO. Even whatever the problem we have discussed just now, this particular problem also they have given. Or if you want to see exactly very similar kind of this problem, you can see Gere and Goodno, first chapter solved example. Instead of this uniform pressure, they have given the point load. Right. Now, coming back to this question number 14. Again, this question is from strength of material. Again, very similar kind of problem we have discussed, and they are continuously asking regarding power transmission. Power is what? 2 pi nt by 60. 2 pi nt by 60. 3 meter long, length is what? 3 meter. We can convert in mm, 3000 mm. It is transmitting the power of 7500 watt at 3600 rpm. What is the required diameter of the shaft? Having the allowable shear stress 100 megapascal. Pi square, they have taken it as to be 10. So first of all, power is equal to what? Torque into omega. Power is what? 7500. Torque we have to calculate 2 pi n by 60. So from here you just calculate torque, that is 750 divided by 12 pi Newton meter. You also know tau is what? 16t divided by pi dq. Tau is what? 100. 16t. 750 divided by pi. That is Newton meter. You convert into Newton mm into pi into d cube. You know everything, right? Now, this particular problem, if you want to solve, so very first of all, you have to calculate what is dq value. What is the dq value? Pi square is 10. 16 into 750 into 1000 divided by 10 divided by 100. So you will be getting dq as 12,000. Now when you take 1 upon 3, you will be getting 22. Sorry, that is 12 pi. 12 is also there, right? Divided by 12. So you will be getting 12,000 divided by 12. So that you will get 1000. Now can you calculate 1000? That is a very simple. Diameter you will get what? Straight away 10 mm. 10 mm. dq is what? 1000. D will be what? 1000. D will be what? 10 mm. These two equation we have to use. Power is equal to torque into omega, and torsional equation. How we got this equation? Tau by r, T by j, tau by r, g theta by L. So tau will be T into r by j. So T into d by 2, j will be what? Pi d power 4 by 32. So that's how you get 16T divided by pi dq. Now coming back to this question, for thin cylindrical cell structures loaded in the compression, whenever they will be subjected to compressive load, the design should be based on buckling strength of the structure. Whenever any material you take, any uh, even a hollow section also is there, but whenever they will be subjected to compressive load, it has to be designed based on the buckling strength of structure, right? Whenever any structural member subjected to compression, axial compression, then we have to design based on the buckling strength of the structure, because usually the length of the pressure vessels or thin cylindrical structures are higher. So whenever the lengths are higher, the chances of buckling is higher as compared to crushing, right? There is a difference between crushing and buckling. So here the straight wire may buckle like this with the application of load P. Whereas you can see that what we find in crushing, just like a when you say cast iron material, when it is subjected to compressive load, it may crack like this. A glass, when you just apply compressive load, it will crush. Usually crushing happen in shortened member, very short members, but whenever the lengths are higher, that will be decided by the slenderness ratios. Whenever the slenderness ratios are more than 80 or 100, then we say it's a long column. When the long columns are there, they may be very prone to buckling failure rather than uh, what we call crushing failure. Question number 17, the governing differential equation for a small deflection. A small deflection is what we have assumed in our derivation of uh, differential equation for bending. Here what we have, ei d square y by dx square, that is what mxx, right? This is what we have equations. So what we can write, d square y by dx square, that is equal to what, m divided by ei. A will be correct. A will be correct, but again you have to think about other options also. Here m, we can write here shear force, that is equal to dm by dx. So now when you differentiate once again this particular equation number 1, so you will be getting ei dq by dx cube, that is equal to shear force, that is equal to v of x. So this is also correct. When you think of further differentiation, w is what we have, df by dx, d shear force, we used to write d shear force by dx. So again when you differentiate, you will be getting what, intensity of the loading, so this is also correct. So all of this, d option will be correct. D option will be correct. Okay, so that's a very simple problem. For derivation and all, you can follow IGC notes, this particular derivation. During this derivation, we have assumed whatever the deflections are there, that is very small deflections. This equation is valid for a small deflections, not for the very large deflections, right? Now coming back to this particular problem of eccentrically loaded welded joints. eccentrically loaded welded joints. The joints which are being subjected to eccentric loading, because from the center of gravity, the loads which we have applied, that is having some eccentricity, So here, whenever you have this type of scenario, how many stresses will be developed? How many stresses will be developed? Two types of stresses will be developed. First will be transverse shear stress. Second will be torsional shear stress, right? Something like this. This is what you have welded joints. Whenever you just apply any load eccentrically, there will be certain amount of load when you transfer here. So it will try to be resisted by both the welds. It will be try to be resisted by both the welds, and it is gonna developing some kind of torsional. It will be developing some kind of direct shear stress. Direct shear stress, and how the direct shear stress will be developed here? So because of this, there will be tau one. What is the tau one? Tau one will be a load. You know that when the load is P, the equally load will be shared in both the members. That is P by two, P by two. The loads which is being resisted by rivets by the welded joints will be what? P by 2, P by 2, because two welds are there. So P by 2 load. And what is the area? Area, everyone know that. What is the area we have? Area, we know that. What is the weakest section in the welded joints? The weakest section will be T into L. T into L, the length of the welds into throat thickness. The length of the welds into what? Throat thickness. Now, what is the throat thickness? Throat thickness, we know that S divided by root 2, where S is what? Leg of the weld. Leg of the weld. Always remember in the problem, leg of the weld will be given to you. What is the leg of the weld? Leg of the weld is what? 10 mm. That is what the symbol we have. You have to always find in terms of T. What is T? Throat thickness. Because that is the weakest section. That is going to fail first. So we have to design safely that particular throat section, right? So tau 1 will be P by 2 into 0.707, because this will be 0.707 times of S into L. P, what is the P? What is the P they have given in the particular problem? P is what? 1000. When you look at into the problem, 1 kilonewton, that is 1000 Newton, divided by 2 into 0.707 into S. What is the leg of the weld? 10. What is the length of the weld? See that, length of the weld. Length of the weld is what? How much of length of the weld is there? 30 mm. Sorry. Length of the weld is 30 mm. So now when you just find, you will find the value 2.35 megapascal, which is approximate equal to 2.4 megapascal. No, 2.4 megapascal. So which option is correct? B option is correct. But if the same problem they would have been asking, how many stresses will be developed? That is the tau one. But there is a one more stress will be developed. One more stress will be developed. That is a torsional shear stress. Consider this to be A, B, C, D. These are the corner points, center of gravity. See, you try to transfer the load. You will find when you apply two loads, one is acting in the downward direction, but this P and this P will create twisting movement like this. And that twisting movement will be resisted by corner points. Join the corner points. See, our problem is over. We got the answer. That's it. But I'm telling you additional data or maybe additional question for this particular problem. How many types of stresses will be developed? So one will be torsional shear stress, like this. Tau A, tau B, tau C. This will be tau D. Right, and here because of this, whatever the the P is acting like this, whatever the force primary or whatever the primary force which will be acting here, it was like this. It was like this. You can see here, right? That was acting primary force. The primary force, because of that, this is nothing but tau 1. That is a what we got here, tau 1 value. The tau 1 value, or you can say all are subjected to tau 1 only. And because of this twisting moment, there will be torsional shear stress will be developed. So there will be torsional shear stress. How to calculate torsional shear stress? Twisting moment into R maximum divided by J. And if you want to find the resultant, then it will be like this: tau 1 square plus tau 2 square plus 2 tau 1 tau 2 cos theta. Whatever the angle which is being included. Whatever the angle which is being included. Right? So that is what we have to calculate: torsional shear stress. Or that is what we are calculating: torsional shear stress. And this is nothing but primary direct shear stress. Two types of stresses will be developed. One is a direct shear stress, other is torsional. And we have to find the resultants. Now, resultant will be, we have to calculate for a section where the maximum resultant loads are acting. Where the maximum resultant loads are acting, when theta will be lesser, tau r will be higher. See that here theta like this, here theta like this. Whenever theta is lesser, so A and D both are critical points. A and D are the critical points. Note down all are these are questions. They may ask same question, but they may ask different data. Maybe they might give different other phases of these particular questions. So that's how we have to calculate for this particular problem. They are asking primary shear stress, not a secondary or torsional shear stress. If they would have been asking torsional shear stress, then this particular problem would have been lengthy one, somewhat lengthy, because moment of polar moment of inertia is not a very easy task to calculate for this segment. Coming back to this particular problem I will do at the end, because this will require a lot of understanding. Without that, you cannot solve about the bolted joints. So what is the preloading and all? For this, I need to discuss that one. Now try to solve this 43 number question. The deflection of elastic member at the point of application of the force in the direction of a force by the derivative of the member's total strain energy. That means if you want to find deflection, then you have to differentiate with respect to the loads which we are applied at that particular point, right? This load, whenever they are acting, there only we are finding the deflections. That statement was clearly given by Castiglione's theorems, right? One more equation note down. If you want to find theta at any point, you try to differentiate total strain energy with respect to the moment which we have applied at that point. Both these statements are coming under Castiglione's theorem, not only for deflections. We have for slope also. For slopes also, we have this the concept of Castiglione's theorem. Do not try to mug up previous year questions. Okay, that's a simple one. Try to see this particular problem. This particular problem, what they are asking. Which of the following is true for ductile material? For ductile material, let me draw a stress versus strain diagram. Most famous ductile material is mild steel, that is a low carbon steel. For that, let me draw. This is what you have engineering stress strain diagram. And if you don't know the points, please note down the points, because at anyhow, in any manner, it will help. A point here, B, B dash C, D, E, F. Whatever we are telling, you have to follow blindly. That is the first thing. Because what we are telling you, I'm telling you based on my experience, which I have given in ISRO examinations, right? And not only if you are reading anything, that may not be sufficient sometimes. You have to read all the other things or surrounding things about that particular topic. Then only you can answer in examinations. Don't judge the paper based on the one or two question or 10 or 20 questions. That simple question they are asking. No. If simple question they are asking, if you are able to answer all of them, all of the candidates will be able to answer those 20 questions. That may not decide the cutoff, or that may not decide the basically rank, merit list. The question that will decide the merit list will be a very challenging one, and that may not be answered by everyone. So here we have our true stress strain diagram will be like this: P dash, F dash. So this is what we have, true stress strain diagram, and this is what you have, engineering stress versus strain. So even you note down the points also. Starting from OA is a linear part of the curve. Point A is basically proportionality limit. Whatever the B point is there, that is a elastic limit. If somebody will be asking you very strictly, Hooke's law is valid up to which point? A point. That's it. Don't try to say B point. A point. That's it. Hooke's law is valid up to A point only. C dash is nothing but upper yield point. C is what? Lower yield point. In any case, for any ductile material, we take this lower yield point to be as design stress. Right? Then you note down CD, whatever the curve you are seeing here. From C, there is a plastic deformation begins in the material. From C, there is a plastic deformations begins in the material. Then D to E is strain hardening zone. What is the strain hardening and all? That is a part of the material science that will be discussed. And then we have EF. whatever the zone you are finding EF, that is a strain softening zone. Strain softening zone. You will find in engineering stress strain diagram, all the curves, basically parts of the curves are having positive slope. See that? Even in fact here also, when you draw any slope, even you take a slope of strain hardening, that is also positive, anti-clockwise. But when you follow this particular slope of this curve, you will find that is having negative slope, right? So they are mentioning the first A statement, engineering strain curve for a ductile material cannot have a negative slope. Wrong. Even what about this strain softening zone? When statement A is correct, that means they are not they are neglecting the strain softening zone, and you know that after necking, the failure has to happen, right? E is what ultimate point, where the necking begins, and F is nothing but what failure points. Failure. Whatever the stress is there corresponding to this, that will be fracture stress or failure stress, right? So that is having a negative slope. Second most applicable failures theory is maximum principal stress theory. Again, that is wrong, because most suitable, I told you, maximum distortion energy theories. Why principal stress theory is not suitable? Because principal stress theory only talked about when sigma 1 is less than sigma maximum or sigma yield, then they are saying that failure will not occur. But we know that ductile materials are very very strong in tension, so there's no point of talking about the those scenarios. This theories of failure does not talk about anything about the maximum shear stress, and we know that ductile materials are very very weak in shear, so that's why it is not applicable. Ultimate strain is the strain at ultimate stress. Yes, this is the ultimate stress point. E is point is what ultimate point. So whatever the stress, whatever the strain is there, that we call ultimate strain at that particular point. That is correct. The strain hardening is represented by negative slope in engineering stress strain curve. Incorrect. C is correct. So this graph is there for, typically I have drawn for low carbon steel, that is mild steel. It is a ductile material, pure and pure ductile material. As you keep on increasing the carbon content, brittleness, whatever the brittleness will be there, that will be start increasing, and maximum to maximum steel can accommodate of carbon is what 6.67 percentage. Beyond that, it will be just come out of the what steel structure. Whatever the steel atoms are there, if you just incorporating more than 6.67 percentage of carbon, it will be simply come out, right? Because maximum solubility of steel to accommodate maximum solubility of iron to accommodate carbon is 6.67 percentage. That's why iron carbon diagram you will find up to 6.67 percentage only. Coming back to this 48th question, for isotropic material, modulus of elasticity in tension and shear, they have given like this. We know that relation E is equal to what 2g 1 plus mu, where g will be what E by 2 1 plus mu. So which is correct? B is correct. Again, that is a very simple. Strain produced in the wire of diameter 6 mm. Strain produced in the wire of diameter 6 mm when it is bent around a large cylinder. When it is bent around a large cylinder of diameter 2 mm, 2 meter can be obtained as by stress strain diagram. How much of stress will be induced in a wire when I bent over it a large cylinder? So one of the good problem, see here, our wires are there which is bent over a large cylinder. I'm just showing you the cross sectional areas. This will be the neutral axis. So what is the y maximum? Neutral axis to upper fiber distance will be, let's say here it is d, so it will be d by 2, where diameter of wire is 6 mm, so y will be 3 mm. Now, and what are the other data? The radius of cylinder, that is also they have given in the problem. Yes, 1 meter. First of all, calculate the strain which is being introduced in the wire because of placing. For that, we have to use the bending equation m by I sigma by y e by r. Sigma by, you focus on these two. Sigma by e, that is equal to y by r. What is the maximum strain produced? For that, we have to calculate y maximum by r. So maximum strain that is gonna produced in that placing of this will be uh, r. What is the y maximum? 3. What is the r? 1000. So that is 0.003. 0.003 means what about this strain at this point? At the yield point. What is the strain at the yield point? That you can calculate very easily, sigma by e. Sigma yield at the what is the sigma value at the yield point? 300 by 200 into 1000. So that is 1.5 divided by 1000. So that is 0.01, sorry, 0.00. How much it will be? 0.0015. And whatever the value you got somewhat double of that. That means 0.003. So corresponding to this particular strain, which is being acting in your particular wire material, corresponding to this, what is the strain? What is the stress value? 300 only. Corresponding to this particular strain from the graph, what is the stress? 300 megapascal. More than 300 megapascal, if you just say more than 300 megapascal, if any stress will be introduced, then it is gonna what? Fail. And what is the deciding value of the what is the failure stress for this particular wire material will be 300 megapascal. Right? Make a note of it. Strain produced in the wire. Okay. Question number 67. When you observe here, try observing. Cantilever beam of rectangular cross sections of depth D, width B, and the length L is subjected to shear force F at its free end. The beam is made up of material which follow maximum shear stress theory. Maximum shear stress theory. Which of the following is true? The beam section has uniform shear stress? No. Why? Because this is incorrect statement. Why? Because whenever we talk about a rectangular section, then we know that because of the direct shear stress, it has parabolic variations. top and bottom it is 0, and neutral axis it is gonna maximum direct shear stress. And the maximum value we know that 3 by 2 times of F divided by BD. That is the maximum value of this stress that you can calculate. At the neutral axis, you can take a fiber. This is a fiber, and you can calculate what is the top maximum you are getting, right? What is the maximum bending stress? That is M into pi maximum divided by I. M is what? F into L into what? Y maximum is what? D by 2. Moment of inertia will be BDQ by 12. So that is 6 FL divided by BD square. In the second option, they are saying at L equal to D by 2, maximum bending stress and maximum shear stress both are equal. Let's see when L is equal to D by 2. 3F divided by BD. Now here you see maximum shear stress is 1.5 times of F by BD, but maximum shear stress both are not equal. When L is equal to D by 2 is not equal to tau maximum. So second statement absolutely wrong. What about the fourth option? Bending stress. No, bending stress depending on whenever you consider, either you consider maximum or you just consider any section, it will be inversely proportional to B. Right. So here again it is incorrect. So automatically this has to be correct. C option has to be correct. Now, how to verify C option? Actually, it is correct. Okay, it is correct by elimination method, but how to justify this? For L equal to L greater than D by 2, any value you take, even you take L equal to D by 2, still maximum bending stress is more than maximum shear stress. So it is a deciding one. Even though you are taking L is more than D by 2, when you take L more than D by 2, put that value, maximum shear stress, that is 6 FL divided by BD square. Now when you put the value, if L is greater than D by 2, what is going to happen? Sigma maximum will be more than 3F by BD. There is no other options. That is absolutely correct. Because see, when L equal to D by 2, we got 3F by BD. But when you put L greater than D by 2, that means 3D by 4 or something like D, definitely we will be getting more than 3F by BD. That is what I have written. Now you divide by 2. Divided by 2. So what will be happening? Sigma max divided by 2 will be more than tau max. So sigma max is what? Sigma max is basically 2 times of tau max. So now here, which is maximum? Bending stress or direct shear stress? Bending stress is maximum. So which one will be deciding? Bending stress will decide the failure stress that we're gonna what put for MSST theory, right? So C option is correct. No doubt. Now we have to understand the bolted joints. Whatever the bolted joint question is there, that question we have to understand very carefully. Now, all of you, please go back to bolted joint question here. Which of the following statement is wrong for the bolted joints? So it is somewhat not a very easy one to do this. Note down, then I will explain. Okay, so note down bolted joints here. Bolted joints. The loads which are acting in the bolted joints, when you follow the loads which are acting in the bolted joints, when you consider any bolted joints, either it may be connected with any other IC engine component or any other component, first of all, initial tightening will be there. We call preload. Second, there will be certain external load. Third will be preload plus external load. Preload plus external load. Both combination can be active. Generally, we tends to do preloading to avoid any kind of leakage in case of pressure vessel. When you connect the flange coupling, when we just apply, let's say two vessels are there, we want to connect, then we connect by bolts like this, flange coupling here. Here we do preloading so that to avoid the uh, leakage of the particular pressure vessels. Here, whatever the statement they are giving, the first one, the bolted joints are preloaded to avoid vibration loosening also. Yes, that is also correct. So that we are tightening so that at any cost, even though under reverse loading condition also or the worst loading condition also, it will not, basically open from that, placed areas. So for the preloading, we are doing for basically avoiding any kind of loosening. You know, so preloading is a very important. How to calculate the preloading? How to calculate the preload? How to calculate preload? How to calculate preload? Note down the values 2840 D, where D is nothing but nominal diameter. Nominal diameter. It is very important. Whenever you consider bolt without preload, there may be loads which are acting like this. See that. This is the level of the load which a bolt may be subjected to, right? A bolt may be subjected to. Here, whatever the deflections. But when you consider bolt with a preload, when you consider bolt with a preload, what is happening? The fluctuation of the load will be this one only. That much of fluctuation won't happen, right? The fluctuation of the load will be not that large as compared to the without. This is the bolt without preload. This is the bolt with preload. This is the bolt with a preload. Note down. Again, some of you might be asking, sir, how, why, and where you are getting this graph. So to explain those things, let me explain you. Uh, this particular topic mostly neglected by gate basically aspirant, because generally this after this topic only the bolted joint question has been started in, especially in the gate examinations. But in other examinations, you have to follow thoroughly the whole bolted joint chapter from the, either you can follow Bhandari or for this, for the initial part of this we can follow Kurmi also. There is no harm in that. Now here, my dear friend, when you just consider the cylinder head, here when you consider cylinder head, the head of the cylinder which is being there by the cover plate, like this. We have the cylinder material. Now these two basically join together by bolts. Generally, what is happening when you tighten the bolt during its functionality, what will happen? The gas will be there. This is a cylinder, IC engine cylinder. The gas pressure will be acting on a head. The gas pressure will be acting on a head. The bolt will be subjected to what? Tensile force. The bolt will be subjected to what? Tensile force. So generally, what is happening here? Whatever the loads which we are applying with the help of gas pressure, that load will be shared by both. That load will be shared by both bolt plus other member. Other member means cover plate and all. Cover plate and whatever the cylinder members are there, right? So whatever the connecting member which are connected to this bolt, they will be also sharing this particular loads which we apply with the help of gas pressure into pi by 4 d square, right? Now generally after doing all this thing, there are so many steps that is already discussed in our IGC classes. When you follow thoroughly this particular steps, you will find the net force which are acting in the bolts, and the net force which are acting in the connecting members. The net force which you will find the resultant load acting on the bolts will be Cp, and the resultant load which are acting on connecting member will be 1 minus Cp, where C is what? Kb divided by Kb plus Km. K and K is what? Is stiffness factor. C is what? Is stiffness factor. Please refer initial pages of the Vibhu Bhandari. You will get what I'm talking about. After doing certain step, you will find this thing, right? Now, my dear friend, what is happening? Understand. Generally, when you do the preloading, actually you are trying to increasing the fatigue strength of the bolts, fatigue strength of the particular bolt. How? Here, my dear friend, what is the minimum amount of load? What is the minimum amount of load which bolt material will be subjected to? What is the maximum gas pressure? What is the maximum gas pressure? That is PR, for example. What is the minimum gas pressure? Minimum is 0, right? Correspondingly, what is the maximum load? PR into pi by 4 d square. What is the minimum load? That is 0. What is the maximum load which are acting on the bolts? CP maximum. CP maximum, right? And what is the minimum value of the loads which are acting on the bolt material? P is 0. So that is 0. So that's how you're getting the fluctuations like this. From the maximum value to minimum value 0. Maximum value to the minimum value 0, like this. FB maximum. That is without any preloading. But when you just apply preload, when you just apply preload with preload, what is happening, my dear friend? Understand. FB maximum, automatically CP maximum will be there, no doubt about that. Plus Fi will also be acting. Fi value is what? Fi value is what? 2840D, where D is what? Nominal diameter of the bolt. What about FB minimum? FB minimum, CP minimum 0 plus Fi, that automatically will be acting. So now tell me, what is your fluctuations? The fluctuation will be taking place between this to this. See that? There is no doubt FB maximum has been suited up, right? That we got higher value, but FB minimum is what? Lower value. So now it is fluctuating from here to here, here to here. Overall, what is, when you ask the designer or design engineer that who is the whether this is a worst loading or this is a worst loading, second one, he will say the first one is a worst loading, where it is fluctuating from a repeated kind of load from maximum to zero, maximum to zero, right? So here, my dear friend, what is happening? With the help of this preloading, we are actually trying to reducing the what, maximum deflection which are happening in the bolt material, and we are increasing the fatigue strength of a material or a bolt material, no doubt. So actually your load has been changes from a repeated load to fluctuated load. fluctuated load. So actually, what is happening? Amplitude of the value of the stress. What is that? Sigma max minus sigma minimum by 2. This is getting reduced by fluctuation. Here we are getting the maximum value of the amplitude, right? Maximum value of the amplitude, but here somewhat lesser value we are gonna get because sigma minimum is 0 in this case. But here we have sigma minimum, at least some sigma minimum that will reduce amplitude values. That will reduce amplitude values. Now, what is happening with the help of these scenarios? When the amplitude loads or maximum fluctuating loads are decreasing, when maximum fluctuating loads are decreasing, overall stress are decreasing, then vibrations in the bolts material are also reduced. Right? Make a note of it. So even though somebody will be asking you why the bolt materials are not designed for dynamic loads, here the load magnitude is changing from maximum to minimum. See that maximum to minimum. It is not a constant magnitude. Then why we are designing only based on the static load? Because here, whatever the values of bolt material, whatever the loads, amplitude loads, that is FB maximum minus FB minimum by 2. This is what lesser and lesser. The maximum value of the amplitude of the maximum amplitude of net load which are acting on the bolt material is reduced from repeated load to fluctuating load. That's why we designed based on the static load. That's why we design the bolts material based on the based on the static load. Now you know that when this fluctuating load, this is a fluctuating load. When the fluctuation will reduce, vibration automatically reduce. That is the common sense, right? And for this only, all this explanation has been there for the first statement. That is absolutely correct. True. When the fluctuation will reduce, vibration will automatically reduce. Right. Again, those who are not believing, sir, I'm not at all able to believe what you're talking about. Then you can take any values. It's up to you. Any value you can take and you can calculate what is the maximum amplitude value here, FV here, and FV here. You will find the differences. A lot of differences. Right. Now, second points, when you just consider threads are made by thread rolling process. Thread rolling process are very highly accurate process, very costly. So whatever the thread profile which we are making by the thread rolling process, they are very accurate and good thread profiles, right? Rather than making over the machined threads, whatever the bolt threads are there, if you made by thread rolling, that is having more accuracy. So again, no doubt that is being preferred. This is again true statement. But whenever the cost is higher, then we sometimes prefer machine thread. When the external load is applied to the preloaded bolt joint, a bigger percentage of that load relieves the compression of the flanges, and remaining percentage increases the tension in the bolt. That is correct. This is also true. Now, bolted joints are designed such that bolt stiffness is higher than the flange stiffness. So, my defend, I told you one statement there. What is the statement I told you? What the statement that I have given to you? The statement which I have given to you, the bolts materials are generally subjected to uh, CP. The loads which are acting, the net loads which are acting in the bolt materials are what? CP. P is what? External load. C is what? KB divided by KB plus KM. KB is what? Is stiffness of the bolt. KB is what? Is stiffness of bolt. Is stiffness of connecting member. Connecting member means flange member. These are all what? Flange. These are what flange members. See that stiffness of connecting member. Now, by this, what you are understanding, when C will be higher here, when you consider 1 divided by 1 plus Km by Kb, Km by Kb, what is going to happen, my dear friend? When is when the bolt stiffness is higher, what will happen? When the bolt stiffness is higher, what is going to happen, my dear friend? When the bolt stiffness value, when the Kb is higher than Km, what is going to happen? This particular value will be higher than Km, then this overall value will be what? Lesser. When overall value will be lesser, C value will be higher. When C value will be higher, the bolt will be subjected to larger value of the stress, and we don't want that to happen. So generally bolted joints are designed in such a way that Kb value should be less than Km. In such a case, Km by Kb will be higher, the ratio will be more than 1, C will be lesser. Understanding my point? All of you are understanding or not? So D statement is what? Very, very false statement, and that is the correct option for this question. Bolted joints are designed such a way that whatever the bolt stiffness should be there, that should be lower than flange stiffness. Flange means connected member, whatever the connecting members are there. Right? Why the flange name is coming? See, the design in such a way that you know that in I section we call this to be flange and this to be web section. This cylinder head is looking like such a way that we tends to say that is a flange member or connected members, right? The whole derivations, how we are getting CP and all, you please refer textbook, right? So that's all for 2017 paper. So you can see the depth in which they are asking in the question paper, right? So they are not doing any kind of joke, any kind of time pass is not happening in ISRO papers. That they are asking very serious questions. Even though in between, if you are finding simple question, don't judge your whole paper based on one or two simple questions. That they are asking very very easy questions. No, if you are thinking and if your preparation is like that, not a very higher level side, then definitely when the paper is easy, suppose for example whatever the question paper will happen after let's say maybe 15th August or maybe before that you have examination of ISRO. Suppose easy paper is coming, very easy, dead easy, and maybe in this scenario the chances is that when you are not attempting a very high number of questions, definitely you may get below cutoff, or maybe you may be getting the marks that may not be sufficient to clear the cutoff, right? Or if other scenario, when you take a higher side, when the paper will be on the tougher side, definitely you, if you are preparing for the lower kind of questions, if tougher question will be coming, then you cannot attempt again that is a problematic situation. So you better prepare for the worst condition, even if it is simple, that will help you. It is not like when you prepare for a very tough kind of question, if simple question is coming, you will neglect that, you will say no, that's a very simple paper. You cannot say in examination hall. In that case, you have to show your whole potential of what you have done preparation, whatever the for the worst scenario you have prepared, that you have to showcase there for the easy paper also. Again, if they ask for the thread loading, you try to refer all the rolling process, types of rolling process in metal forming process, in metal forming chapters. That's how the method of learning, or solving the question, basically what we are observing from the previous year questions. Same question won't be asked. Thread rolling can be asked separately. Again, they can ask what we call, I told you, right? Bolted joints are always designed based on the static load, not on the dynamic load, right? So that also you can keep it as a note point somewhere. Note down here. The reason I told you, whatever the amplitudes of the loads are there, that amplitude value is lesser and lesser because of the preloading. Bolted joints are always designed based on static load, not on fluctuating load. As amplitude of fluctuating load decreases by preloading. Preloading means certain kind of tension force automatically has been applied to the bolted material. So that's all for 2070 paper. A good number of questions they ask. In fact, one or two questions are very, very highly appreciable questions. You can see this strength of material question. In fact, this was also, somewhat maybe shocking for some of the students. Primary shear stress, because we tend to forget the formulas for eccentrically loaded welded joints, riveted joints, bolted joints. If you want, I can thoroughly explain you whatever the eccentrically loaded welded joints, riveted joints, bolted joint separately in another class. All the three four cases of bolted and riveted joints, they are almost similar. Only the in case of bolted joints, a diameter will change. Core diameter, nominal diameter will be there, but in the riveted joints, only diameter of rivets will be there. Welded joints separately, we have the cases. This is also one of the good problem. We tend to, the moment they frame this question, we always stick. We think that it is a composite bar section, and we tend to say strain in both the blocks will definitely will be same straight away. You will say, but when pressure is same, if area will be different, then whole scenario would have been different. But area also they have said the same, stress will be same. When the stress will be same, then this Hooke's law has to be valid. That is the assumption for any material that is being followed in the strength of material. Okay. Okay, guys, thank you.